3, 2, 1. Once we develop the polynomial for e to the x, you're going to have to memorize it. So let's go ahead and do it together. So we've got f of x is e to the x. And of course, that's another name for the 0th derivative. Yeah. Oop, I made my 0 too small. There we go. And now the center near 0. So we're going to center it at 0. Let's write that up here. The center is 0. That's the center of the approximation. That's the point of tangency, essentially. So what is f of e? I'm sorry, what is f of 0? It is e to the 0, which is 1. Okay. The first derivative is e to the x. Holy moly, smokers. So f prime of 0 is also 1. The second derivative is e to the x. So the second derivative at 0 is also 1. I think I see a pattern here in Taylor's form. It looks like the numerators of all of my terms is going to be 1. So I don't really need to expend much effort going much further than this. So I think I'm ready to write the third degree polynomial. So I'm going to say e to the x is approximated by, let's use, Ryan, you had another letter yesterday you wanted to use?
And W.
Okay, W, and it's a third degree. So we're going to put sub 3 of x, and then here we go. Let's start by, again, getting the habit of writing the tangent line. It's the y value, which is 1, plus the slope, which is 1, times x minus the x value, which is x minus 0. Okay, so it's just x. There's the tangent line, right? And now it'll pick up the pattern. So plus, now we're on 2, 1 over 2 factorial times x squared plus 1 over 3 factorial x cubed, right? So again, if you want, you could say that this is 1 over 0 factorial times x to the 0. This is 1 over 1 factorial times x to the first, so on and so forth. I'm not going to tell you not to keep the pattern, but we can build on something that we already know how to do. Tangent line. All right, so that's it. So we have the squiggles there. And of course, we can use this third degree polynomial to approximate values of e to the x, which is transcendental, near 0. And that could be useful for something like evaluating a limit. Let's try it out. If I were to evaluate this limit, never not first, we use direct substitution. What do we get? We get 0 over 0. Now we could lop it, but let's try it a different way. Let's try substituting this in for e to the x. So I'm going to say that this, I'm running out of room. This is going to be approximately then the limit as x goes to 0 of 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Oh, by the way, what would the next term be? Do you pick up on the intrinsic pattern pretty easily too? Boy, howdy. It would be minus 7 over sine of 32, right? I'm really bad at patterns. This is probably the easiest pattern out there, right? 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. It doesn't alternate like the other three we've seen. It's pretty handsome. So we plug that in there and then we get minus 1 all over 2x. Now, if I simplify, the ones cancel, right? And once the ones cancel, I can, bless you, I can factor out an x from the top. This is our very first method we learned, right? Fado, because you still get 0 over 0 once you plug in. You won't write that again. The Fado, factor and divide out. So we get 1 plus x over 2 factorial plus x squared over 3 factorial all over 2 times x. And what happens to the x's? They divide out. They're gone, like a lot of the stuff in the senior hallway, unfortunately. Some of it got, I want you to know Miss Lincoln went to fight for y'all. She got a lot of that stuff back.
I know.
Yeah, including Reno's picture, which is now back up. Apparently, I saw it, but it's very wrinkled. It's very wrinkled. But anyway, that's called theft. That's called looting. That's criminal activity. So anyway, once we get rid of the 0 over 0 problem, now the world again is safe again for direct substitution. So if I plug in the top, I get 1 plus 0, which is 1. And in the bottom, of course, I get 2. So the answer is 1/2. Okay. Now, is that the actual answer? What's another way to do it? Let's see. Let's come over here and try it the other way. Method 2. It's good to have multiple ways to do something, right? Like if you're like, dang, I'm skinning this cat the way I normally skin it, but man, I just can't get the skin off this one. Well, try the other method. Oh, thanks. The skin came right off. More than one way to skin a cat. Like, where did that phrase come from? I don't know, but we're going to lop it. Lop it. Exclamation point, colon, right? Limit as x goes to 0. Sorry, I amused myself right there. That's kind of self-indulgent. I apologize. The derivative of the top, what's the derivative of e to the x minus 1? E to the x minus 0. And the derivative of the bottom, 2x is 2. Now we use direct substitution. We get e to the 0, which is 1 over 2, and presto magic. There you go. Well, because I wanted to show you that, you know, there's another way, right? In case you're skinning it one way and the skin gets stuck. Use the Taylor polynomial to get the skin off, right? Just another way. It works. That's what's cool about it. It verifies that it actually works. Okay. All right. Is this surprising? No, it's not, right? Because as we're learning, that's what Taylor polynomials are designed to do, right? To mimic transcendental functions near the center. And the more terms you have, the further out from the center you can deviate. Okay. Let's get one thing straight here. The function e to the x and w sub 3 of x, they share the same value at the center, which in this case is c equals 0. Okay. Other than that, or outside this, they only approximate each other. If I can spell that right, they only approximate each other. So if you remember way back in the day, I said a function and its tangent line share two things at a point. They share a y value and they share a slope. Okay, that's the same thing here. Any function and the Taylor polynomial that represents it, they're going to have the exact same value at the center. And that's true for all of them, but they only approximate it outside of that. That's an important idea that's going to carry forward when we get to series with infinite terms. Okay, but sometimes infinite many terms is a direct copy of the original function, not just a good clone, a good impersonator. Okay, all right, example 7. I'm glad we did this yesterday when I asked you about the concavity over here. I don't know where it was, but I said it's gonna. Anyway, let's just do the next one. You'll see what I mean. Example 7. Given that p sub 2 of x is a plus bx plus cx squared. It's a second degree Taylor polynomial for the function f, some function f that we don't know about, centered at 0, right? It says about 0. So we could also call this a what polynomial? If it's centered at 0? Maclaurin. There you go. Maclaurin. What can you say about the signs of a, b, and c if the function whose polynomial this represents is pictured over here at the right? Justify your answer. Okay, so if this is f, and we're centered at 0, here's 0 right here. What can we say about a? Let's do these separately. A, b, and c. Can we say anything about a? Is a positive, negative, 0, undetermined? It's positive? Why? Why is a positive?
It's got a positive y and
Yeah. Remember what I just said? They all share the same y value at the center. So the y value of f, in other words, f of 0 is positive. And so when you plug a 0 in over here at the center, p of 0 is going to equal a, right? And so a has to also be positive. Yeah. It has to do with the shift. It's the y-intercept. So I know a is positive. There you go. Boom. What about b? Is it positive?
it's got to be negative
Why?
because it's concave down.
What's its concave down?
The graph
Of
of
f. Just say f is concave down. Pure words. Okay, so F is concave down, so B is negative?
Yeah, because C can't be 'cause it's squared.
Oh,
Big difference.
right, right.
Yeah,
Yeah, I would agree with you that F at 0 is increasing concave down. Does that tell us anything about B and C?
I think B is positive, C is negative.
Yeah, there you go. There you go.
Oh.
Okay.
Oh,
So-
it's not C squared, it's X.
Here's an easy way to systematize the process when you have maybe functions that are larger than x squared. Remember that a is the constant. So it is going to be the 0th derivative at 0 over 0 factorial, right? That's how we get the constant term. B is the linear term. So B is going to be the first derivative at 0 over 1 factorial. And C is the squared terms coefficient. So C is going to be the second derivative at 0 over 2 factorial. Okay. So we're kind of doing it in reverse. We've done it forward where we figured out what those were and we made the polynomial, but now we need to kind of go backwards. So if we were to simplify this, A is basically F of 0. And we could pick up on that based upon that little fact that they have the same they have the same value at the center. Now we know F of 0 is positive, so A is also positive. So that takes care of that one systematically. If I simplify this one, B 1 factorial is 1, right? It's positive. So I know B is whatever F prime of 0 is. Now F prime is the what of the graph of F there? It's the slope. So the tangent line there, right there, M is greater than 0. So I know this is greater than 0. So yes, those of you who said that, B is positive because F is increasing there. And then we know that 2 factorial is positive, right? So that's not going to affect the sign. So the sign of C is only affected by F double prime of 0. Well, F double prime of 0 is the what of the graph of F there? The concavity, right? And we know that the concavity is negative. So this is negative. Yeah. There we go. So the Y value is the constant, or the denominators in the Taylor's rule don't matter because they're positive, right? So they don't affect the sign. So really, it's just the Y value, the slope value, and the curvature value that affect the sign of A, B, and C. Okay, that makes a nice multiple choice question. Or it doesn't, but it does. It does. Okay. Sound like Uncle Schmedley from SeaWorld. All right. Google it. Google it. All right. Letter 8. Letter 8. Letter 8. Thank you. Thank you. Yeah. So here's what's cool about Maclaurin series. Sometimes we don't have to reinvent the wheel. I can piggyback on certain series that I already know to create new and improved series. The series that we should know, I say series, but I mean polynomials, that's what we're looking at right now, that we should know are these guys. So let's come down here to the bottom page since it's the last one and just write these out, okay? Sine of x is going to be approximately, what's the first term in the Taylor series or the Maclaurin series? 1, right? And then minus x to the first plus x cubed over 3 factorial minus x to the 5th over 5 factorial plus x to the 7th over 7 factorial. Okay. And I'm going to stop right there because I put an approximation. Okay. You'll see in the next section that we can actually put plus dot dot dot, and then we can put an equal sign there, but not yet. So there's sine. Cosine, of course, is the derivative, but you should know it outright. Cosine starts with what? -1?
0.
0, okay? Plus, minus. I'm just going off what y'all started me off. I'm going back up to the first one, and I'm not really happy with it. Sine is an odd function, right? It has origin symmetry. So all my terms have to be odd. That's odd, that's odd, that's odd, that's odd, but 1, there is no 1 there. Yeah. It doesn't start with 1. Okay. It starts with x. 1 is an even function. Think of the horizontal line y equals 1. It has y-axis symmetry. So now that's gonna change all the signs, isn't it? Yep, it is. So it's x, positive x, minus, plus, minus. There you go. Now cosine is even. So cosine starts with the constant 1, and then minus x squared over 2 factorial plus x cubed, not x cubed, x to the 4th, sorry, over 4 factorial, minus x to the 6 over 6 factorial, so on and so forth. Okay, so there you go. Memorize them. Odd, x to the first is the first odd term, 1 is the first even term, and they alternate after that. Okay, odd exponents, even exponents. And then we just met this guy. E to the x is approximately 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. And I'll stop right there. You get the pattern. All right. So the first two terms don't have the same pattern as the others explicitly, but they do in their genetic code. Right. So memorize that one. So if we have these memorized now, we can actually change these. I already showed you that we could take the derivative of these to get new functions when we took the derivative of sine. You can actually take the antiderivative of these as well. But what else can we do with these? Well, we can build off them by either A, substituting something in for x, like replacing x with 2x, or B, we can multiply them by either a constant or even another variable, or we could do a combination of the two. Okay. So if I told you to create the, let's see, write the first 4 non-zero terms of the Maclaurin polynomials. Maclaurin means the center is where? 0. Yeah, and all the ones we wrote below are centered at 0. You'll be able to spot them if they're not centered at 0, because instead of x squared x to the 4th, it would be x minus 3 squared, blah, 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 x minus 3 to the 4th, blah, 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 and there the center would be 3. Okay. You wouldn't want to have to, I mean, you could, but you wouldn't want to have to like regenerate all your terms like we did with e to the x to start the class and then create it using Taylor's form. You certainly could, and you'll get the right answer, but it's a little bit faster if you do this. Okay, let's write out sine of x. Sine of x is approximately the first 4 non-zero terms. We'll do it again. This is a chance to get it right. What's the first term in sine? X. Good. And then minus x cubed over 3 factorial plus x to the 5th over 5 factorial. There's 3 terms, so one more. Minus x to the 7 over 7 factorial. Make sure you got a squiggle for the polynomial, because if you accidentally put an equal sign there, you're going to lose a point on for your response. Okay. Well, let's go ahead now and substitute x with 2x. Okay. So I'm going to now put g of x, which equals sine of 2x, is going to be approximately parentheses minus parentheses cubed over 3 factorial plus parentheses to the 5th over 5 factorial minus parentheses to the 7th over 7 factorial. And what am I going to plug in where I left the blank? 2x, 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 2x. And guess what? That's it. That is the four term, the 7th degree Taylor polynomial. It has 4 terms, right? This is where we want to kind of maybe make the distinction. When we talked about series, n equals 0 or 1, n equals 1, n equals 2, n equals 3, n equals 4. There's 4 terms here, but it's a 7th degree polynomial. So if you were to name this, you can name it like q sub 7 of x if you want. We name the polynomials off their degree. Okay. Now that's not the simplified version, of course, is it? If we wanted to simplify it, you could say now that equals 2x minus 2 cubed is 8. You get 8x cubed over 3 factorial plus 2 to the 5th, that's 32x to the 5th over 5 factorial, so on and so forth. 2 to the 7th would be 128 x to the 7th over 7 factorial. And if there is an implicit pattern there, you know, maybe you see it, right? We just keep multiplying the top by 4. Yeah, by 4. 8 times 4 times 4 times 4. So you could generate the next term if you wanted.
When you drop down to the next line,
Uh-oh.
are you allowed to put that?
Yeah.
That X equals?
Oh, yes, I can. Yes, I can, because the sequence is sine of 2x is approximately this, and this is equal to that. So yeah, I can. Yeah,
But you couldn't bring sine 2x.
but no, you couldn't bring sine of 2x down. Yeah, that's a good point, right? So if you want to keep bringing down the squiggles, you can.
Okay.
Yeah, because yes, that's the sticky point of equality, right? Because that's equal to that. But if I were to work left to right, see, like I did with Q of 7, I could easily do that and put an equal sign and bring that over there. So it is kind of a gray area. I'm glad you mentioned that. It is kind of a gray area. Once we say squiggle once, typically if we work down, we don't have to keep saying squiggle. Okay, because the chain of custody would always have to pass through the line. So sine of 2x is approximately that, which is equal to that. This is equal to that, which is approximately that. Now, if it's totally equality and they're equals all the way down, then of course this could follow down. That's a real finer point of discussion, but you saw it and you recognized it too. So thank you. Thank you. Those are good questions. Those come from paying attention and being alert and thinking. I like that. Right. Yeah. Oh, by the way, speaking of reviews, just FYI, this morning we had another review. I did 2 more free responses from last year's free response group, and tomorrow I have a chiropractor appointment at 7 o'clock, and so tomorrow's is going to start at 7:30. I'll be down there as soon as I can, depending on how much Dr. Stamps wants to talk. I'll try to be here as soon as I can by 7:30. But we'll just do one question tomorrow, 7:30 to 8:05, 8:15 at the most, and we'll do one more question from the free response. Okay. And then next week I'll go back to I might maybe next week, since I'm doing morning and afternoon, maybe I'll do like free response in the morning and multiple choice in the afternoon, or versa versa. Okay. I like that. And I'm recording all of them. I haven't had a chance to record the one I did yesterday that I accidentally deleted, but I'll get to it. Okay. So you can watch them on your own. And speaking of watching on your own, remember that you also have, if you're going to stay on schedule, the schedule that I made for us, you also have viewing assignments every night. Now you can binge on the weekend like you do with any good Netflix series, right? Or Hulu series or whatever. But tonight's viewing homework for Wednesday is 1 video. Okay, example 6 through 7 from 6.1. Okay, so there is a little bit of time left. If you notice, these videos go through 5.5, and I typically don't have you watching stuff over the weekend, or I do actually on Friday. If you watch it Friday night, it's not weekend homework, but you do have the weekend to catch up. Some days, you're welcome to watch ahead, you're welcome to watch backwards, but this is kind of the schedule that we need to stay on for y'all to get through everything. And if we finish chapter 9 early, then I'll come back and I'll pick up and start emphasizing some of the stuff from mainly chapter 6. Okay. We learned the disk method for volumes this morning in the review, and I did it really quickly. And that might be enough for some of y'all to see it once and get a feel for it. But if you watch the videos and maybe work 1 or 2 from the worksheet, it'll work. Okay. So anyway, coming to the reviews will also help. As someone said, it's kind of a forced way to get you to do problems, right? Instead of just sitting at home, you're here, you're working along with me. All right. So g of x, we got x times cosine of x. Now, if we were to generate this one from scratch, it would be kind of a nightmare, because every time I take the derivative, I'm going to be using the product rule, right? Yucky, gross. But hey, I am allowed to alter existing polynomial representations that I have memorized by not just substituting in for x, but for multiplying through by a variable or a constant. So let's go ahead and write out cosine of x first. Cosine of x is approximately 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. There's 3 terms, so I need 1 more, minus x to the 6th over 6 factorial. And now I will multiply through by x. So g of x is going to equal x cosine of x, which will equal I'm sorry, will be approximated by. Now I can either write all that and put an X out front and then distribute, but I'm going to distribute as I go, if you're okay with that. So distributing an X, I get X for the first term minus X cubed over 2 factorial plus X to the 5th over 4 factorial minus X to the 7th over 6 factorial. And wow, that is, I mean, you're already done with the 4-term representation before someone else is really even on their second derivative, probably setting up the machinery using Taylor's rule. Okay, so it's kind of nice, kind of nice. And again, if you want to verify these, maybe in the privacy of your own home, you could graph X cosine of X in Y1, and you can graph this in Y2 and kind of hit zoom 6 because they're centered at the origin. And you'll actually see the polynomial wrap itself around X cosine of X, and then it'll depart at some point. Okay, kind of a cool idea. All right, and then g of X. This one is a combination. I'm replacing X with X squared, and I'm multiplying not by a variable, but by a constant multiple. So let's write out e to the X first. E to the X is approximated by 1 plus X squared over 2 factorial plus X cubed over 3 factorial. There's the first 4 non-zero terms. And now we'll say, so g of X, which equals 4e to the X squared. If you want to do this in 2 steps, you can. Sometimes it's hard to kind of create it in 1 step. So let me go ahead and do that, actually. Let me go ahead and do the replacement first. I think that's probably the first one I would choose to do. So I'm not going to call that g of X, but e to the X squared then would be approximated by 1 plus X squared plus X to the 4th over 2 factorial plus X to the what? 5th or 6th? 6, right? Power to a power, you multiply, and you can also look at the patterns of the exponents. All right, now I'm going to take that and multiply by 4. So that's what I can call g of X. That equals 4e to the X squared. And I'm going to distribute as I go. So 4 plus 4x squared plus 4x to the 4th over 2 factorial plus 4x to the 6th over 3 factorial. And again, you might be able to simplify some of those terms. I'm sure 4 over 2 simplifies and 4 over 6 simplifies. But the point is that you can create things from existing ones. And if there's more than one thing, it might not always be that easy. Some of y'all probably could have pulled off replacing X with X squared and distributing it 4 at the same time. I have no doubt. But remember, the more things you do in one step, you're not communicating it as well. And that's part of the goal. And you're also opening up yourself for unnecessary, careless mistakes. Mistakes. Yeah. What do you call a female sirloin? Mistake. Yeah, I just made that up. That's good, right? Okay. Yeah. There you go.
Call a female with one leg.
One leg. You can call her anything you want. She's gonna hop over to you. Is that what you're?
Eileen.
Oh, Eileen. Come on, Eileen. All right. Oh, a BC. Algebras. What do mermaid mathematicians wear? In Hank's dreams. Golly. Algebras. Yeah. Okay. Yeah. It sounds itchy. All right. We're done. That's why we're telling jokes, right? So I'm not going to go on to the next section, but you do have worksheets that are awaiting you. So whatever time that's left, you can work on the 9.2 worksheet. We'll start 9.3 tomorrow.
What's your Harry Potter?
I don't know anything about Harry Potter except his name. I've never read the books. I've never watched the movies. I don't get any of the illusions. I have no costumes for Harry Potter. I'm not a Star Wars fan. I don't know any Star Wars things. I don't have the Incredibles gear. And what else? I don't know anything. This was a hard one for me. So I just went college day. Yeah, I went college day.